Everyone knows parking in Auburn is a big issue. And so there are, in fact, two startups in Auburn dedicated to solving the problem. So the first one is Parking Grid Technologies, who won the Tire Cage Challenge, which was the Auburn version of Shark Tank. And their goal is to identify open parking spots and output them to an app so that users can find open parking spots. They claim that the problem in Auburn is not enough parking spots, it's that you can't find the ones that are open. So they sense where their cars are and using data analytics tell you where the spots are and output an app so you can find it. And so if you look at their website, they actually have these big sensors in each parking spot that they want to sense, which to me seems like a big waste of money and resources installing things and having sensors for each parking spot. There's another startup in the Auburn Research Park working on the same problem, but I don't know the methods or the name of their company. So we'll focus on this one. I want to solve the same problem of localizing the open parking spots using OpenCV, which is open camera vision, because you'd be able to mount a camera on existing infrastructure or by using existing security cameras to accomplish the same task without having to install hardware at each parking spot and having the time to go and install that. So the first approach I use uses the Hoff transform, and I overlaid a circle into each parking spot with the idea being that I could train the camera to look for those circles with each circle representing an open parking spot, because if a car drives over the circle it's no longer visible and you won't be able to see the circle. So each circle that it senses identifies an open parking spot. If I change the number of cars in the parking lot, it kind of works, but with this first solution I'm getting some false positives based on the curvature of the car. So this blue car, the windshield radius is pretty close to the radius of the circle I used to mark the parking spot. So you get a false positive there and a false positive on the black car above. What I did was take this information from the parking spot, and by knowing the coordinates of the spaces, I can train the program to only look in those spaces for the circles. So that was my second attempt at the problem. So again, the program identifies the parking spots that are open when there are no cars. But unlike the last solution, I changed the number of parking spots. Since it's only looking in the specified area where I told it the spots are located, it prevents the false positives from occurring. And I can change this to any parking spot, so there are no spots available, and you can see it prints to the command line that there are no spots available. If I do 2 cars, it should give me 6 spots available and tells me the location and radius of the circle where they occur. So I just want to go through some of the code and explain how I got this working. I did this program in OpenCV, which is open source, and I used Python, so it was my first experience in either one of those languages. So this is the program for the first solution I had, which gave the false positives. So the code up here tells the user how to use the program. So you call the function with Python and access the image. Then it imports necessary packages it needs to use and shows how to use the argument how to parse the arguments. The next step is starting to read the information, the visual information from the picture. So I read the image in, and then I resize it to width of 480, and then I keep the dimensions with these next three lines, keep the original proportions, with the idea being that the smaller picture I have, the faster the computer can process it. And I don't need all that extra information. So I resize it, and I create a copy to output and write on. And then I convert it to grayscale because color images have a lot of extra information dealing with the colors. And then I apply a blur to the image to soften the edges of the circle to make it easier to identify. So I use a Gaussian blur, which weights the pixels. So here I'm using 7 pixels to blur. So in either direction, the middle pixels being blurred, and it blurs it based on a Gaussian distribution. So the pixels that are closer affect the blur more than pixels that are further away from the area of interest. The next step is to take that gray image and detect the circles, which is stored in a variable or array called circles. And so the first argument calls in the picture, which I called gray. This CV2 Hoff gradient is actually detecting the edges. These second two parameters, so this parameter that is identified by 1.8, basically has to do with something called the accumulator. But the higher that value, so if I changed it from 1.8 to 2, it would detect less circles. If I dropped it, it would detect more circles. But that's kind of a finicky parameter. The number 75 has to deal with the minimum distance these circles are apart from each other. So again, if I lower the area or lower the value to say 50, I'll detect more circles, but also risk getting more false positives. These parameter 1 and 2 also have to do with the gradient and the accumulator values. I typically leave those alone. The most important values are this minimum distance, which is 75, and then the final two arguments of this function are the minimum radius and the maximum radius. So after running through the program identifying the circles, I found that the radius of the circles I constructed were 24 to 25. So I set the program to only look for circles in that range. So I gave it a little bit of leeway with 23 and 26. After it detects the circles, it rounds it up to a radius, rounds up the coordinates and radius of the circle to an integer. And then over those circles, it draws a green circle and an orange rectangle on the center to show where the circle has been detected. So again, let's go back to our image. You can see the original image on the left side, and the right side it detects the circles and overlays a green circle and a orange square on the center of that circle. And then I output the image to the window. And again, I'll go back and show that this is creating false positives. So this black car, this white car, this blue car, and this other white car are creating false positives because these circles it's looking for are similar in radius to the circles of the car's windshield. So if I go to the solution that eliminates the false positives, I use the first trial to create an array of positions. So I know where those circles are, and using this circular location array, I got a point, a coordinate for each circle. So this 348 by 358 is the coordinates for one of the circles, and there's 8 of them, along with their corresponding radius. I did the same thing I did before. I loaded the image, resized it, changed it to a grayscale image, and then I blurred it. Then I created this count function to count how many circles it found. So I loop it through this for loop, and I look in all the locations in the circle loc variable where I saved the known locations of these circles. And then I created a mask. So the function of the mask is to put an overlay on the image so I'm only looking in that one spot. And that does two things for me in this instance. One, it reduces the amount of processing I have to do on the computer side because the image is much smaller and I'm only looking at 8 of them. Two, I know where the circles are, so I can only look in those specific locations for the circle. So I don't have to worry about the car unless it parks right over the circle, which is unlikely. And even then, if it did find a false positive there, I could edit that out or tune it out by changing different parameters. So when I find a circle, I add one to the count of circles, and then again I draw a circle, a green circle, and an orange rectangle in the middle of the located circles. And then I output the number of spots available and show the output image. It's very simple code and very powerful. You can imagine this being used not only for this app, but for autonomous cars. You can integrate it into a network of sensors so a car can drive and know where to park itself based on the open parking spots. You could use it in a warehouse to put packages. Say if you're Amazon and you have warehouse space, you have robots moving stuff around, you can locate the empty warehouse space or shelf space with something using this method and have robots move to it. Now that I've proved that this works with still images, the next step would be to incorporate this into a Raspberry Pi and camera module. OpenCV runs pretty well on Raspberry Pi, especially with the new Raspberry Pi 3, which has a 1.2 gigahertz quad-core processor now. So it's plenty strong enough to do this kind of image recognition, and I would create a real parking spot or parking lot to scale and use Matchbox cars to be able to process this information in real time and show that I can move cars in and out of the parking spots, and it will show open or closed parking spots, or open spots or non-available parking spots. Once it is working on the Raspberry Pi, you can try this method full scale on an existing parking lot on campus.